So now we're taking a look at experimental probability. It's based on actual events or experiments that have occurred. So we're often looking at a table of values and coming up with a probability based upon the table. So in example 7, the table shows the results of a spinner experiment. Find the probability of spinning a 4. So we have to add up for the total number of times that we spun this spinner, and we get 50. So the probability of spinning a 4 is 14 out of 50, or in other words, 0.28. For the next one, find the probability of spinning greater than 2. Well, there's still a total of 50 times we spun the spinner. Spinning greater than 2 means spinning a 3 or a 4. So we're going to take 19 and 14 and add those together. And so that's 33 out of 50 for an answer of 0.66. Example 8. The table shows the results of choosing one card from a deck of cards, recording the suit, and then replacing the card. Find the experimental probability of not choosing a club. Well, if you're not choosing a club, then that means you are choosing hearts, diamonds, or spades. And adding the hearts, diamonds, and spades together, we get 19 out of a total number of cards that we chose, which was 26. Example 9. The student council is selecting a president, treasurer, and secretary from their 6 members. What is the probability that John, Jacob, and Jingle are all on the committee? Well, we first need to figure out what are the total ways we could select these 3 members for president, treasurer, and secretary out of a total of 6 people. So 6 permutation 3, because the order in which we select these 3 people for president, treasurer, and secretary makes a difference. So 6 factorial divided by 3 factorial to give us 120. So when finding the probability that John, Jacob, and Jingle are selected on the committee, we have a total of 120 ways we could select any 3 members out of the 6. Well, we want John, Jacob, and Jingle to either be president, treasurer, or secretary, but we don't care the order in which they're picked. So we're going to have 3 factorial divided by 120 because there are 3 factorial ways that we could be successful because we just care that they're on the committee. And so there's 3 factorial ways that could happen. And that gives us an answer of 0.05 chance. So experimental probability is usually a lot easier than theoretical because you have some actual data tables to refer back to when calculating the probability. Now we're going to talk about geometric probability, which is determined by a ratio of lengths, areas, and volumes. So in example 10, a point is chosen inside the larger square. What is the probability that the point is also in the smaller square? So we're going to look at the probability of our total space is going to be in the bottom, and the area of the small square is going to be in top. Well, the area of a square is the base squared, or base times base. So the area of the entire figure here would be 6 times 6, which is 36. The area of the small square is 2 times 2, or 4. So our probability that it lands within the small square is 4 out of 36, or in other words, 1/9. Example 11. So here we have a circle. It says a point is chosen at random in the figure below. What is the probability that it lands in the shaded region? So first, we need to find the area of the large circle. Then we need to find the area of the small circle. And then we need to find the area of the shaded region by subtracting the 2 above. Area for circle is pi r squared. So I'm going to have pi times 8 squared for the area of the big circle. So that's going to be 64 pi. Area of the small circle would be pi times, now, the radius of the small circle is the difference between 8 and 3, because 3 is the radius of the shaded part, and 8 is the radius of everything. So the difference between those will just give me the radius of this small piece right here for the circle, small circle. So that would be 5 squared, or in other words, 25 pi. So my shaded region is 64 pi minus 25 pi. And that gives me 39 pi. Now I left things in terms of pi because when I'm calculating the probability that this point lands in the shaded region, I have my total area, which is the big circle, 64 pi in the bottom. The shaded area is 39 pi. And the really beautiful thing is that those pi's divide out, leaving me with 39 over 64 as my answer. So sometimes it works out to not write things in decimal form. All right, very last problem in the 7.2 lesson. Example 12. A point is chosen at random in the figure below. What is the probability that the point lands in the shaded region? So we have several shapes we need to find areas of. We need to find the area of the big square. We need to find the area of the triangle. And we need to find the area of the little rectangle on the inside. Area of the big square would be 9 times 9, in other words, 81. Area of the triangle, 1/2 base times height. So 1/2 times, let's see here, 9 times 9, which is 40.5. Area of the little rectangle would be 3 times 4, giving us 12. Then we need to find the area of the shaded region. And that's the triangle minus the little rectangle. So 40.5 minus 12 to give us 28.5. So finding the probability that a point randomly lands in the shaded region is the area of the shaded region, 28.5, divided by the total area, which is the big square, so 81, to give us a probability of 0.352. All right, so this wraps up theoretical, experimental, and geometric probability. Please let myself or Mr. Brasser know if you have any questions.